Let's go ahead and give a warm good morning welcome to Mark, who will be presenting Cosmic Turtles of Code, its graphs all the way down. So please give Mark a warm welcome.
Thank you. All right. Thank you. Hey, everybody. I'm Mark. I'm super excited to be here. Today I'm going to be talking about this cosmic turtle that we all write atop and how its graphs all the way down. So I'm going to start by giving you a little bit of introduction. I've been working in code security for over a decade now. 2 jobs ago, I was working building fuzzing tools. A job ago, I was doing security consulting. And then I went and started my own thing, doing a little security consulting, but also writing tools for both security folks and developers. But about me personally, I've always thought that visuals are super exciting and really helpful. But as a security consultant and security reviewer, really the motivation for this talk came from the intersection of those things, because I was always interested in how can we understand code better, faster? Like, what tools can we use? What are we not doing? And like, what's the limit? How could we get to the point where we can understand code as fast as humanly possible, which, like, security reviewers obviously get that. And so this talk is really exploring a lot of the ideas and sharing the ideas. And so I didn't come up with the foundational concepts of this, right? A lot of it's old stuff, but I want to share it because I don't think it's talked about enough, and I think it can really help people. A lot of it is visuals, but it's not just visuals to make a pretty picture. I think it's cool when we can make something that is both useful or beautiful and useful, especially in the security context. A lot of the security or RE problems, they're really just understanding code problems, and maybe it's understanding it better than the person that wrote it, but maybe it's just understanding it so we can apply our own lines of thinking against it. And keep in mind, everything that I'm talking about here, I'm not talking about completely replacing everything we always used to do. I'm talking about doing things in a new way that might help as a supplement. So first things first, let me talk about, when I say graph means a lot of things in the English language. Not talking about bar charts. Sorry if you came here to learn about graph databases. We're talking nodes and edges, or vertices and edges, if you prefer. And even within that, I'm talking more specifically about directed graphs. There's different kinds. This shows sort of a range from generic to specific. DAG's always stuck out in my head. I don't know if it's just me. I think that people like the word. It's easy to remember. But actually in practice, cycles are really common. And so I don't end up using them a lot. So when I say graph, I'm talking about directed graphs pretty much for most of the presentation. But let's talk about how we write code. So this is how we write code. We write functions. It's text. This is nice because it works the same way that we read. It follows the normal rules of reading and writing, top to bottom, left to right. But if you wanted to actually sort of draw out how this code can execute, how we flow through, you'd actually end up with a picture, right? This is a control flow graph. It shows that if and else conditions as lines out of these nodes. And this, I think, is pretty helpful because it actually shows like what is the structure of the code. But everybody's used to reading code one way. Except if you're in the RE community, you might be really familiar already with control flow graphs. This is the same equivalent function as it would be shown in the control flow graph view for IDAPRO, Binary Ninja, and Ghidra. And so they all follow the same rules, and you can see the same general like layout decisions. You have blocks, you come in at the top of the block, go all the way to the bottom, and then potentially there's multiple ways out. So that's if you're looking at a single function. But if we're looking at multiple functions, this is where things get tricky, because to read this code and understand the flow of it, your brain has to jump between the name of a function to the definition of the function. And that's just a little bit harder. And so even though this code has less lines of code than the previous one, this one's actually harder to put together in our heads what that picture is. Like, how many of you had that picture in your head after reading that code for 10 seconds, right? For me, my brain just relaxes a little bit when I know what the picture's supposed to look like, and then I'm just matching the text to the code. And so this is a call graph, and they can flow either left to right or top to bottom. It's really just a preference thing. So I want to try this out. Read this code, but don't focus on understanding what it does. Instead, think about how you're reading it. And if you can't read it that well, the token highlighting has very helpfully highlighted all the function names in yellow. But this is what the graph actually looks like. And so if you were like me, when you started reading this code, you were looking for those function calls. You were looking for the relationships between functions. Now, maybe you started looking at arguments and how they flowed through the functions, or you were looking at how the return values bubble back up. But really, this is a great example of how if you started with this map, it's a lot easier to read. And actually, I can make this example a lot harder to read without changing any of the contents of the code. So I want to note real quick that this is kind of a static call graph because it shows what can happen. But if we recorded what happened when we ran it once, that would be the sort of dynamic as it ran view. And so when you run it, you can only ever execute 4 of these 6 shown functions in a single run. So that's kind of the difference between static and dynamic. Static shows everything that can happen. But if I'm going to make this harder, the first thing I'll do is I'll mix up the function order. So if I had shown you this at the beginning, it would have been much harder to read. And it's just because your brain has to keep track of locations, and now these locations aren't order. The next thing I could do that would make it harder to read would be to split these functions across files, because the further we separate these functions, the harder it is for our brains to understand the connections between them. And then the last thing I could do is I could insert functions that are similar but not actually related to these ones, and that would even further throw you off, because then there'd be a whole bunch of chaff that you'd have to pick through to figure out, okay, but the functions that I care about, which ones are those and how are they connected? So this may sound like I'm exploiting the weaknesses of the human brain, and because really that's what those problems are, they're brain problems. But this is just how people write code. In a normal code base, nobody is out there topologically sorting their code in call graph order like this. But they could, I guess. I mean, if somebody wants to write a linter for topological sort, go nuts. So this is sort of the structure, right? So there's a lot of other graphs, a lot of them especially related to behavior of code, but I'm going to focus on call graphs and control flow graphs because those are what really describe the structure of code, and I think that that's sort of the first place to start and the most helpful thing to talk about when we're talking about understanding code, because understanding code is really the motivation here. Now, to talk about where we are, it can be helpful to say, how do we get here? Now, control flow graphs, control flow graphs, I mean, those date back to the 70s. So that idea has been around forever, and people have been writing tools to sort of show what code looks like for about that long. And so there are a ton of tools out there that make either control flow graphs or call graphs. This is not a new concept at all, tons of them out there. But I think that the RE community is probably the ones that really went hardest after them and made them part of their core workflows, because the control flow graphs work even at the machine code level. So you don't need to have anything about the code. You can be looking at pure assembly, and control flow graphs still work, and they do help you understand. At least I think so. I know that there's some people that learned to RE reading linear assembly, and they still prefer that. But so IDA Pro, I don't know when exactly they added these features, sometimes in the aughts, had both a call graph view as well as a control flow graph. And then a few years later, these Dynamics folks came along, and they had some really awesome ideas. They built tools around these graph ideas. And this was, I'm trying to remember exactly when they started, 2008-ish, 2010-ish. They worked for a while, maybe even earlier than that. I know that they'd been developing these ideas for a while, but so these came basically with IDA, but a little bit after. And these guys were way ahead of their time. I found myself, I discovered their work a little later, and I found myself reading these ideas from a decade ago, and I'd be like, dang, these guys already had this idea. They made it work a long time ago. But they were very focused on RE. They did a lot of great things. But the thing in particular that I think that both IDA and Dynamics did really well is that they saw this idea that if we can take this information and make it accessible to be scripted around, then that makes it so people can build all sorts of crazy things on top of what we've already built. And that's super powerful. And so that brings us to today. One of the things that I wanted to do was play with graphs. And I wanted to do that with Binary Ninja because that's my RE tool of choice. They have a really nice API. But I didn't know what graphs I wanted to see in the beginning. So I knew that I needed to make it scriptable, something that was easy. I also wanted it integrated already with what I was doing. So I wrote Ariadne, which is a plugin. It uses NetworkX, which is the standard Python graph library. So if people are familiar with Python graphs, they probably already know these things. And you can see a screenshot on the right. The idea was to make it inside of Binary Ninja, but at some point they stopped shipping a web browser inside of Binary Ninja. So now, so now you have to run it in a browser beside it, but it still works, right? And the one thing that I'll call out on this graph, just in terms of explaining the visual, is you notice that the node sizes are different. And just for Ariadne, I was writing it for fuzzing purposes, but one of the big things I noticed was it kind of helped me to be able to zero in on bigger, complex functions. And so this view is larger nodes are more complex, which is also heavily correlated with size. But so this was a graph helper for a tool that already had a graph API. I get it, right? More than one person was like, why did you bother writing something? Yes, lots of graph utilities exist. These ones on this slide, there's graph utilities and RE frameworks that have graph utilities. And you can do whatever you want. I just wanted something that had sort of live updating with Binary Ninja, and I could customize it. So really, as long as you can customize it, like, use whatever you want. But this is a quick GIF of the basic workflow, which was like, hey, as I navigate around on the left side in the Binary Ninja UI, I want the graph to change. So this is sort of similar to IDA's proximity view, except that it's live updating as I move around. And the visualization itself is pretty interactive. I can click on nodes, and it'll highlight the functions that it calls as well as the functions that call it. You can see at the beginning, there are some nodes that are orange colored. Those are imports, and then I can hide those. And so it's all about sort of being able to do a couple of tweaks to get to the graph that I wanted. And so that shows like the basic use case. One of the big motivators for me was, hey, can I use this to RE faster? And this is one of the things I figured out because I tried this out on CTF challenges, and I was like, well, CTF challenges are real small, and so I can end up seeing like a lot of the whole challenge real quick. And so you can see on the left, this is like the normal decompilation view, and then if you were to graph out what you can see from that one view, you get that middle picture, and then on the right is kind of like what I actually wanted to see, which is the quick overview of this tiny binary. Now, if you're like me, your first thought is, well, I'll just graph the whole thing, especially if it's small. But this is that same binary, which is a toy-sized challenge binary, and it's like, oh, wow, that's a lot of code. Well, luckily, it's interactive. I can just zoom in, right? And like, okay, let me zoom in a little bit more, and like that's like all the way zoomed in, and I can see main, like maybe a couple other functions. Clearly, this is, you can't just look at the whole call graph, right? And you might be tempted to think that this is a layout problem. So this is, the same graph with a different layout. And it's like, well, okay, this is a good layout, but what is good? It's optimized for certain things. It turns out call graphs are just kind of ugly. Like, no matter how good your layout is, this is like a tool that was custom written to show gigantic graphs. And I think this is a beautiful picture. If you look in sort of the middle to the right, you can see a star being born, I'm pretty sure. But so this is a really cool picture. But my question is what could we use this for? For the code understanding purposes, I don't think this is useful. But the question of usefulness is helpful. So again, talking about workflows, what does this help us do? I think that the find and grep workflows, those are great. Those aren't going away. We're really good. We've been trained by all of our tools to navigate forward and back refs, whether that's in source or in an RE tool. But I think that graphs give us a different view, and they do take a little getting used to. It's a little bit more interactive, at least until we figure everything out. But honestly, this is about adding potential tools in the toolkit, and use Ariadne if you want. It's open source, so you can look at it. But use whatever works for you. Like that's the big takeaway here. I'm just trying to show these ideas. And so let's talk about applications for these ideas. On both the sort of attack and defense side, we have this idea of reachability. We want to understand, okay, there's this piece of code, but how do we get there? And static control flow analysis is kind of the first start for a lot of this. How do we, this is the code of interest, how do we get there? And you can do this within an RE tool or within an IDE, right? You can say, okay, show me all of the references. Where does this get called? But as soon as you start to go a couple layers back, then it's hard to keep it organized in your head, especially if it's just text. So let's talk about an example, this was a real piece of code from a binary that I found a bug in, an old CVE, where I was like, oh man, this is definitely an injection vulnerability. But it starts with a receive, and so the question is, like, how do I get here? And so the first thing that you want to do is that static control flow analysis, source sync. Start here, get there. And so we can actually show in this binary, this is how entry point all the way to the function that you care about. Great, okay, first question answered, it's reachable. This is a simple example. It's not always this easy, but this is a real example because it was that easy. Now, on the defensive side, you might be coming out from a different view, which is, hey, maybe there's a function in a dependency that has a vulnerability, and we want to understand what's our exposure to that vulnerability. The first step of that analysis is typically what we just talked about, find the back references, what functions call it, and then start to go back from there, understand those paths. That's what we saw in the simpler example, but sometimes you end up with more complex things. And this is the same CTF binary I was talking about, and this was based on a real issue that I was trying to look at in this binary. And the question was, how are these two functions related? Because they both access a file, and we can see that because they both call read. And so the question was basically, can data that's read in read token, does it ever end up in send file? Because this could potentially indicate privileged information that would later get leaked out. But this graph doesn't show that answer. And so in order to figure out what graph we want, this is where the interactivity and the experimentation comes into play. So I'm not going to, a lot of this is done via scripting, and I'm not going to focus on the scripting. If you go to the Ariadne repo, there's an example that's very similar to this. And so I'm doing this with scripting, but I'll just show the pictures because I feel like it's a bit easier to follow the pictures. So the first idea is, what if we sort of zoom out a layer and start to look at the local neighborhood? We can see these same two functions, and I've used those two colors to try to keep the association clear. We can see, yeah, there's a connection. On the right-hand side, I've highlighted the read call, and you can see, yep, those two functions, they still have that same shared connection to read that we saw. But if you look to the left at the parents, you see that there isn't a clear connection between them. Like, we don't see a shared parent or ancestor node. And so my first thought is like, well, maybe the connections between them, they'll travel through the graph, but it might not just be, source sync, because it's not always related that way. And so if we treat the graph as an undirected graph and then just use network X and say, show me the shortest paths, you can do that. And you'll find that there is a short path, but it's not the one that you want. And so, all right, step two, we don't want to look at the descendants of these functions. We want to look more on the parent side, the ancestor side. And so how do we describe that in graph? Well, if we take the ancestors of both of these functions and then show where they intersect, I just realized that I put union when I meant intersection. How embarrassing. That is the right thing that we want. We want to see, well, I guess it is, it's not either of those specifically. But so this is the picture that we wanted, long story short. And so you can see, okay, they do have a shared parent, and that's main. And so really, if we want to understand the data and see if there is any way from stuff that gets read in read token to ever end up getting sent out via send file, this is now the graph that we need to look at. And this is where you would dive in and look at the control flow graphs and really try to understand. That's where the RE work or the code understanding work comes into play. But once you have this as a starting point, it really makes it a lot easier. So let's take a step back and talk about this. You still have to read the code, right? I ended by saying, well, now you have to go figure it out. The grep and the forward and back references, still viable, still useful. But I think that one of the trends that I've seen is that a lot of people want to just turn this over to static analysis, sort of automagic tools. Like, well, they just tell me where the bug is, and then I go look at it. And the problem with that is that static analysis is a really hard problem, like capital H hard, right? It's not solved. Static analysis is imperfect. So you're either going to always, so it does help, right? You should try to find stuff automatically if you can. But there's going to be times when you either miss stuff that you should have found, or that it tells you something is a problem and it isn't actually a problem. So you still kind of always need to have these manual helper tools, and that's really where I think that graph workflows can help, because they help the human understand the problem, and that's really what I'm about. So if you're looking for LLMs, sorry, there's another talk. I'm about empowering the humans. So the next application is one that really motivated Ariadne in the first place, which was I wanted to find bugs with fuzzing. And one of the observations I had, well, if you can find complex code that hasn't been fuzzed and you fuzz it, chances are you find bugs. I don't think that that's earth-shaking news to anybody. But so if we look at it, if we wanted to see the picture of it, the fuzzer, by its nature, coverage-guided fuzzers are always going to try to discover more code. They want to try to reach more code. They generate random inputs and run the target to try to tell when that's happened, but that's what they do. So in theory, we should just be able to throw up a call graph and then see where the fuzzer has reached and where it could reach. And so with Ariadne, using BNCov, which is another plugin I wrote, we can bring in coverage data. So in this case, it's block coverage data. It just records what was the code that actually executed when you ran the target in this way. And so in the context of a fuzzer, you have a specific input, you run the target, you get the coverage information to show what code actually executed when I ran it with that input. And so so we use BNCov to get that data, and then we overlay it with Ariadne. So we've got our static call graph that shows everything that could happen, and we use the dynamic coverage data to show what actually happened. And the reality is that if you run fuzzers, you will discover that you miss a lot of code. And a lot of that code you miss is either because it's dead code or just because configuration issues. Like if you look, a lot of the first column of gray nodes, the ones that aren't reached, they're all related to sockets. And when I was fuzzing this code, I wasn't using the socket mode. So none of the socket code's ever going to run, no matter how clever I get with inputs, right? That's reality. But being able to see this at first allows you to say, like, OK, I get it. That's not important. But our goal with this kind of visualization is to find what's the code that hasn't been covered at all, or what has been very covered suboptimally, and find those things. And so the visual, according to the legend, the sort of vertical fill indicates what percentage of the basic blocks in that function are covered. And so we can see on the right-hand side, if we look at this node, it has several child nodes that are either uncovered or they have very low coverage. And so this one picture gives me a great, okay, where do I need to go to make this fuzzer better? First stop. This one picture did that, and like I think that's pretty powerful. That's pretty helpful. So if we want to walk through that workflow, though, of like, okay, so let's pull the thread on that. Let's understand why this is happening. Handle HTTP v1 is the function in question, where we've got one child node that's not covered. So let's start there. Let's try to understand that. If we look at the control flow graph, with BNCov, you get basic block highlighting to show you all of the blocks that are highlighted. There are other tools that do this. Lighthouse is one. But in this case, basically everything that's colored, the blocks that are colored, and they're reddish in this picture, are covered, and the gray blocks are not covered. So we look, yep, there's one basic block in this switch construct. That's what the sort of horizontal line of boxes is. This one block, it contains a call to handle HTTP v1 post, and it's not covered. And so if we look at the switch to see why didn't we ever get there, the value to the switch construct comes as an argument. So we've got to go back up the stack in the call graph and figure out, okay, where does that value come from? And it doesn't come from handle HTTP v1. But if you go up one more level, you see its parent, handle HTTP request, has another child, parse HTTP request. And that is where the magic is. In parse HTTP request, it has a child, translate request type, that if we look at that control flow graph, we see a very similar thing, where we've got a lot of covered blocks, but one that's not. And if you look at these blocks on the left here, this is a succession of string comparisons. So it's comparing a string to specific things like head, post, put, delete. And if you're familiar with HTTP, those are the HTTP verbs. And so yeah, what this is showing is that out of everything the fuzzer did, it was not able to find an input that would get that edge to the gray box. And so post requests aren't being covered, and that's why handle HTTP v1 post wasn't being called. And this is the workflow. So we were able to cover sort of all of these nodes. The data propagation is highlighted in red here, and see, okay, in order to help our fuzzer get to the next step, we needed to sort of understand all of these functions. Now, if we start with this picture of having the overview, it's a lot easier to traverse those functions, keep in our heads where we're at, and understand what we need to do next. So I think that this is a really helpful thing, but I don't want to misrepresent and say that graphs solve all your problems. There are definitely times that things don't work out, and I want to share one of those. So understanding patches is a pretty common workflow, because in the RE community, if a patch comes out but it's not clear what the bug is, well, you can look at the patch and understand potentially what the bug is. The dev community, they just start with source, so that's a lot easier, right? Good idea, if you got it, right? Just look at the source level diffs. But I wanted to look at a complex bug. So there was this libwebp bug that had a fair bit written out about it last year. Ben Hawks had a good blog post explaining this bug. It's pretty complicated, right? It is a complicated bug. And so my question was, can we use graphs in any way to help us like understand the bug or the patch or the code? Or is there going to be something that's difficult here? So we start with the diff. 4 files changed. Now, in the big scheme of things, this isn't a crazy big commit. Like, this is a decent bit of code. The picture on the right shows how far I had to zoom out to fit it in one window. So you can see that there's quite a bit going on here. But we do get some help from the commit message, which says, like, hey, out of bounds right in this function. OK, cool. Well, that's a good starting point. And we can go through and look at all of the functions that are changed. And so we can do call graph diffing or just map the changes from the commit onto a graph and simplify it, sort of say, OK, what are the functions that are affected? Now, with Ariadne, this isn't like a feature that's built in and easily works. I was able to do it with that. But essentially what I did was I compiled 2 binaries, one before the patch and one after, looked at the code, did some highlighting. It was a bit manual, right? But this picture at the end of the day, I think, does kind of help cage your understanding to, okay, this is the code that we're talking about, right? These are all of the functions that are important, and these are the ones that are new. These are the ones that changed. So I thought, hey, let's look at the coverage, right? Let's run each of them, and you can see, yep, there's 2 new functions, and those new functions got called. Probably not a surprise. I was like, all right, well, let's keep working. If maybe we can look at CFG level stuff, see differences in coverage. And so same deal. The covered blocks are the red ones here. And what I found was you can see some differences here if you look really closely. But this is, it's not as helpful as I thought. And when I dug deeper into why that was, I mean, one of the big issues here is that for these functions, they get called multiple times. And with basic block, like highlighting these blocks on the control flow graph, they don't show the order that these things happened. It doesn't say, hey, this function got called 4 times. On the first time it got called, like these blocks executed. The second time, these ones. It's hard to show that ordering. And that's really like a problem with pictures and trying to cram data into visualizations. So I was like, all right, what else can we do? Let's reproduce the crash, compile the binary with address sanitizer, get our specific locations. It does give us very specific locations. This is where that data was allocated, and this is where the out-of-bounds write happens. If you look really closely at the text here, those are the same functions that we saw in that graph. So it's like, OK, that graph is helping. We can point to it on the graph and say this is where that happened. And indeed, in the control flow graph, same deal. We can point to like those addresses. But this is a complicated bug. And so overall, I would say that this was not really a success. The call graph diff does help. And there are other tools that can give you stuff like that. But let's talk about why it wasn't as helpful. So with this bug, it's focused on heap data. And so it's dynamic. It can be allocated and freed in different places. And the lifetime the lifetime matters, like where it's allocated and where it's used and where it's freed. But it's harder to show these things on these graphs because they don't really show time, right? Also, the patch involved changing structs, just, different data structure. And if you change structs, yeah, you might see changes in your graphs because like there's new functions that allocate and free those structs, which is what we saw. But that doesn't really communicate much about the bug itself or the patch itself. This is something that I think is pretty, it's a different problem, right? These graphs don't show, these structs don't show time. And so one of the big takeaways that I wanted, or one of the things that I wanted to investigate was time-dependent information on these graphs. So when Microsoft's Windebug has popularized this phrase, which has caught on a little bit, time-traveling debugging. Very interesting. But all that means is that it records the trace of whatever you ran and then allows you to replay that trace to give you the feeling of forwards and backwards debugging. So the question is how do we visualize stuff like that? Well, yeah, you just break out your pie plot and just make yourself a graph there. We can record the address of every instruction that executes, and there's our scatter plot, right? And this is kind of interesting because you can see horizontal bands there, and in the lower right-hand corner, that's the actual binary that was being run, and those other addresses that are up higher is like all the libc and the setup stuff. So it is kind of funny. You do get some information about that, but clearly that's not the end-all, be-all. One thing so let's explore a few different things on this topic and see if we can collect some ideas here. One thing that I saw years ago that I was really interested in was in the DARPA Cyber Grant Challenge. They had this view that they called the filament view. And so it did the same thing as that graph that we just saw, where it's recording the addresses over time that are executed, but it's plotting those on a Hilbert curve, which is in the upper right-hand corner, and sort of extruding that to give you a 3D view. And so this is pretty cool to look at. I remember seeing this for the first time and being like, dang, that's a really good idea. But let's talk about what it's actually used for here. The primary use of this visualization is comparison. And so we can see that in the lower left-hand side. If I recall this, what's being shown here is two versions of a binary being run sort of in the same normal way. And then, so on the lower left, the red trace is a patched binary. And in this case, the patch broke the binary. And so what they are showing is, hey, the binary stopped running early, and then the unpatched version, it would have continued on and executed all those things. And so at a high level, yeah, you can compare those two binaries. And comparing the execution of two binaries, by the way, is kind of a unique thing. So it's kind of cool to see that they're able to do that. But this tool, it was really built so that the developers could make these really cool 3D like fly-through explanations of things. And that's kind of cool too, because it is sort of an animation, and it does explain sequence of things. But if you're just going to look at it as a static picture, it doesn't really work. But it does have a lot of information here. And if you look in the lower right-hand corner, it's hard to see, but they do have some pictographs that show when specific things happen, like communications, when the binary stops running, stuff like that. But there's actually already a pretty common way to show what code executed over time. And it's called a flame graph. I thought that this was like a really well-known thing, but I'm always surprised when people haven't seen one of these or don't know how to read them. So no shame. This is a really cool visualization, so I hope if you haven't seen this before or know how to read them that I can help. Basically, the amount of time that is spent in a function is represented by its horizontal width. So if you look at, this is the main function right here. I don't know if you can see my pointer. You can't. So the main function is about the fourth row up, and so there's like, 80% of the graph to the right. That's all that happens in main. And so what you can learn just from looking at that is like 20% of the time during this execution was not in main. It was in setup code. And so this is kind of a cool idea because it represents unique call stacks. It represents time. This is even, you could look at this as a representation of a call graph, a dynamic call graph where instead of edges, you see vertical stacking. So like main calls reader loop, and instead of having like a node with an edge, you've got main and then reader loop stacked on top of it, and then the size of the nodes corresponds to the percentage of time. So this is actually a call graph too, right? And that, I remember the first time I thought about that, I was like, oh, that kind of blows my mind. But what most people don't know about flame graphs is that they're interactive. And they have been ever since they started, as far as I know. You can zoom and filter. And so this animation here shows me zooming in on main so that main expands to take up 100% of the width, because that's all I cared about. I didn't care about stuff outside of main. And then what I do is I type in a package name, because this is Python code, and then I see all of the code in that package highlighted. And so this is actually like even more powerful than I thought at first. I think many people thought. And this is a great example of an interactive visualization. Now, this, I've said 100% of time and percentages of time. Flame graphs are built to profile code, so you can profile the execution of something, and whether that takes, 10 microseconds or 10 seconds, the percentage stays the same. It's meant to show us a profile. So it's not really meant to show multiple things, like it's not as good for comparison. This is a one thing at a time kind of view, but it is very cool. Another very cool view is a tool called Tenet, which was written by Marcus from Ret2 Systems. He's over here. This was inspired by Kira, but I think that there's a lot of really cool stuff that's done here. So one of the things that I want to call out is like the use of colors and controls is very smart, multi-tier timeline. I think that the big thing here is the ability to pivot. So if I want to see the next time this address gets executed, I want to pivot on the execution, or if I want to see, hey, when this address is important, is like it's a pointer, when's the next time someone reads from it or writes to it? Being able to pivot on addresses like that is a very powerful thing. And I think the other thing that I really want to call out is using an RE tool as your front end is a really smart idea, because all of the users of that tool already know how that works. Plus, those tools are meant for detail, right? And so a few more tend to add some widgets, but using an RE tool is a really smart idea for your front end, which it works. It was written for IDA Pro, but I have had people tell me that the Binary Ninja port also works well. So definitely check that out. I will say that this is another tool that is meant to explore one trace at a time. So the next question is, how do we explore multiple executions? So naturally, I thought of fuzzing, because I've done a lot of fuzzing work. A fuzzer runs the target multiple times, and it's literally going to discover new code as it runs. So like, let's show how it discovers new code. And this is something that I wrote. It's proof of concept sort of animation thing, because I thought, oh, well, I'll just animate it. And so when a block is first discovered, it's red, and then sort of as it gets older relatively, it fades to blue. So this is interesting because it shows the idea, but again, without the concept of order, it's harder. I think that this is an instructive thing to look at, but without like literal paths, this can be a harder thing to reason about. So this is neat. I think that it's an interesting idea, but it also raises questions that I think are useful to ask about, like how to show time. So the idea of animation is kind of the first thing that a lot of people think of when they think of, oh, you're showing something over time, just make an animation. It changes over time. But the way that our brains work is that we're not great at recalling previous stuff. So if you make an animation, if you ask someone to compare in their head what 5 seconds in was compared to when it started, that's actually a really difficult thing to do cognitively. And so in this case, there's a little slider bar that I made, so you can sort of see it tick over each time a new input is added. So being able to control that is nice, but then it's a question of like, well, how are you showing time? Because this doesn't show wall clock time. So it's an interesting question. And this view, you could expand it out to multiple functions, but then you kind of run into the problem of, okay, well, are you just overwhelming people with scale? Like, what are you really trying to show here? So this does show that coverage grows over time. Mission accomplished, but I think that there's other things to talk about. One thing that I wanted to, that I looked at is live CTF. So live CTF is a head-to-head speed CTF. This last year, it was held in conjunction with the DEF CON CTF, But the format is that you'd have two players playing head-to-head the same challenge, and we would record their screens, and so I helped organize this. And so we would record their screens and then show what they were doing like a live sportscast. And we had people give a sportscast-style commentation. And I thought this was a really awesome idea the first time I saw it, which is why I wanted to get involved. And this is super entertaining, and I think it does help to have people sort of talking through, hey, these experts, they're moving really fast at solving these problems. So it does help to have someone who knows something about it to say like, oh, look, they found the bug, and like this is what they're doing now. But the question is what can we show people to help them come along for the ride, both experts and lay people. So one of the obvious things is tool use. If you're familiar with the tools, you could understand, hey, these are the tools they're going to use. If you're not familiar, you could say, okay, so there's three kind of categories here. They're reversing in IDA, they're writing an exploit script in VS Code, and they're running and debugging the target. Those are sort of the three general tools. And so in the lower left here, I made a timeline that shows that idea, where just different colors show different tools that they're running. And then I added this idea of a checkpoint, which, again, if you're familiar with the problem, it's a binary exploitation problem. They're going to have to like find the bug, figure out how to exploit the bug, and then capture the flag, right? Those are the three steps here. And so I made checkpoints that I kind of arbitrarily came up with in terms of what that looks like. Went back and looked at the footage and then mapped out every second to say, okay, this is what they did each step along the way. And this is cool because you can see, hey, player one who ended up winning, as soon as they got the crash, they never went back to IDA. They stopped reversing right there, and everything they did was all writing their exploit script and debugging the target. And so that's kind of an interesting thing to say. But I was also thinking, like, well, how do we do this with graphs, right? So I had this idea, well, let's just take the call graph, and then maybe we can just watch the attention of these players. Because for at least, I don't know, almost 50% of this challenge, we've got people who are looking at IDA. And if all the viewer takes away is like, oh, they're looking in IDA. Like, great. What does that mean? Like, are they good? Are they making progress? And so I've put a red X on where the bug is, just in case you couldn't tell from the graph. But like having that sort of thing is neat because at least a layperson would be able to say like, okay, the bug is over here, they're not looking at it, but maybe they're like getting closer to it. I thought this was an interesting idea. And we can also put the terminal and VS Code as nodes on this graph, and then we can animate it. And I apologize for the potato quality, but this is a proof of concept animation. Now, it's kind of cool. Like, yeah, this is sped up a little bit. These guys do move really fast, though. But we can see that the idea of just putting a current highlight and moving it around is a little bit disorienting because it doesn't show history. And so this I thought was an interesting thing to do. We've seen other things in the past have either like fade red to blue or highlight intensity, stuff like that. I think that these are steps in the right direction. But the big takeaway is that there's a lot of cool things we can use graphs for. It is cool because graphs show the structure of the code, but ultimately you have to choose what you're trying to show somebody. You really don't get to show everything all at once. You want to choose, hey, is this an overview thing or is it an interactive thing that someone's going to like look at and then they're going to drill down and really understand the task at hand. If you're trying to compare two things, like make a visualization that makes that comparison obvious and easy. If you're trying to drill down into one thing, make it interactive. And I think that we're going to continue to see this idea evolve, especially evolution of execution over time. This is a really cool picture I saw from an academic paper. But again, I was like, that's a cool overview. But so what we've talked about, graphs, call graphs, control flow graphs really help us see the fundamental structure of code. We can use a number of workflows leveraging these things. I think that these are great supplements. A lot of people like this stuff, but they don't have the tools to use it. If you're interested in these ideas, definitely come talk to me. I'd love to hear your ideas and figure out what problems you want to use them for. I think that there is any tool works kind of philosophy. Yeah, there's a lot of graph tools out there, and all of them probably can do this stuff. So find what works for you, and I think that the future is just going to contain more interesting visualizations, and I hope to put out more stuff along those lines. So that is it for this talk. Do we have any questions? You just raise your hand and yell it out, or there's mics too. Anybody? Okay, question was, have you thought about porting this tool to Ghidra? Yes, I have. If you want to help me out or send me a pull request, please come and talk to me because I'd love your help. Ghidra, I will give it a shout out. Ghidra's built-in call graph thing is, I think, the best of the three major RE frameworks built in. Okay, sounds like there's no more questions. If you want to talk to me later, please. Oh, wait, we got one more person getting up for a question. Have I done any exploration of what in fuzzing? Flame graphs and fuzzing. Question was, have you done any exploration of flame graphs and fuzzing? A little bit. So the flame graphs are interesting because it shows where the code is spending a lot of time. And I think with fuzzing, you can fuzz for performance, but generally that's not what people are doing. Now, certainly, if you wanted to make your fuzzer more efficient, a flame graph could definitely be used for that, and that would be an interesting thing. I don't think I've seen anybody talk about that. Because like if your fuzzer's spending all of its time in some garbage function that you don't care about, then like make it so it doesn't do that. All right, thanks. Cool. Well, I love to talk about this stuff, so if you've got ideas or you want to send me pull requests or anything else, I'll be outside. Please come talk to me. Otherwise, have a great con.